Let's get started. So the Fibonacci sequence, many of you probably already know, and although it seems basically just a set of numbers, it actually has a variety of interesting implications. A Fibonacci sequence is formed with a series of numbers known as the Fibonacci numbers. Today's talk will cover the definition, properties, applications, and generalizations of the Fibonacci sequence. Fibonacci numbers have a deal in math because they produce intriguing mathematical patterns that are closely related to a special value observed in math, known as the golden ratio. Patterns are seen in nature, from human body, the physiology of plants and animals. They are also used in art and architecture to create aesthetically appealing designs. How are Fibonacci numbers defined? First rule, the first terms are defined as f0 equals 0 and f1 equals 1. You may have had this sequence be presented to you with f1 and f2 equaling 1. And Fibonacci also initially defined it starting from f1. Regardless, either way produces the same sequence. Subsequent numbers are obtained from the formula shown by the equation below, in which the two numbers right before are added together to obtain the next number. Here lists the first many terms of the sequence. And you can even take a look at the parity of the numbers and observe that every third term in the sequence is even. You can see this by mapping out the terms based on the parity. So F0, which is 0, is even. F1 is odd, and F2, even plus odd, is odd. And odd plus odd is even. And then odd plus even is odd again. Continuing, it's seeing a pattern, even odd, odd repeats. Since the parity of the term depends solely on the two terms right before it. Therefore, as you can see, among any three consecutive terms, exactly one is even. Let's learn some history behind the sequence. The exact date of origin of the Fibonacci sequence is unknown. During around 200 BC, the Fibonacci sequence appeared as a pattern duration of syllables in Indian poems. The formal reference of the sequence appeared later, though. In 1202, Fibonacci introduced the sequence in his book Liberace, in which he showed that rapid generations duplicated in accordance with the Fibonacci numbers. In his hypothetical rabbit setting, Fibonacci considers the growth of an idealized rabbit population. He assumed that at the start, a single newly born pair of rabbits, one male, one female, are put in the field. Starting at the age of 2 months, they gives birth to a male-female pair, and they continue to produce a new pair every month onward. And rabbits never die, so that pairs would continue to produce another pair each month forever once it reaches 2 months of age. question that can be raised is, how many pairs will there be in 1 year? Oh, I mean, like a chat. Yeah, that's young, right? Rabbits mature much quicker than humans. So how many pairs will there be in 1 year? We'll use a diagram to assist us in solving the question. In January, a pair is placed on the field. Since it takes 2 months for a pair to mature, the population in pairs will stay at 1 in February. The pair will produce another one in March, giving rise to originally 1 pair plus newborn pair, which is 2 pairs. In April, there are the 2 pairs of rabbits from March. That's another pair that is given birth to by the initial pair. Red pair does not produce another pair that month since it is only 1 month old. In May, there are the 3 pairs from April. And 2 new pairs are produced by the 2 pairs existing in March, contributing to 5 pairs in the field. Now, and that also happens similarly in June. Now, can you see a connection between the rabbit experiment and Fibonacci numbers? I'll give you a couple minutes to do so. Yeah, it seems like some of you already have the correct answer. So we'll go over it now. Maybe you have gained some sense into how the circumstance connects with the Fibonacci sequence. Notice that the number of rabbit pairs in the field at the end of the nth month is n. Consider just the new baby rabbit pairs in the nth month. They must be equal in number to the pairs of rabbits that mature enough to give birth to baby rabbits. This, of course, is precisely the total number of rabbit pairs alive 2 months ago. Now, the total number of rabbit pairs in the nth month is the sum of the number of pairs alive in the previous month. And the number of new baby rabbit pairs. Thus, this produces the Fibonacci occurrence. And since this holds where n is 1 and n is 2, it works for all natural numbers. And it can now be calculated that in a year, there would be F12 or 144 pairs on the field. Important methods to demonstrate the Fibonacci sequence geometrically is through the Fibonacci rectangle, which can be constructed by tiling squares with side lengths following the Fibonacci sequence. It can be seen that the figure is comprised of squares with side lengths following the values of the Fibonacci sequence. Starting from two squares of side length 1, take the side lengths of the two squares to make another square of the side with the side length that's held aligning with those two squares. So 1 plus 1 is 2, 1 plus 2 is 3, and 3 plus 2 here is 5, and so on. The rectangle should grow indefinitely with construction of squares, as the Fibonacci sequence can go on boundlessly. We'll just go here 34, then 5, and so on. The Fibonacci spiral is created by drawing circular arcs connecting the opposite corners of squares in the Fibonacci rectangle. If you look first, I'm going to show you the animation. So after looking, we have gotten immersed in it. It is beautiful. We'll dive into how the Fibonacci spiral rectangle connects with nature and how it resembles two other spirals. First, we're going to jump to the golden ratio, which is relevant to the Fibonacci sequence. When a line is divided into two parts, if the longer part divided by the smaller part is equal to the sum of lengths divided by the longer part, then the ratio is known as the golden ratio or golden number. So you can see here a showing of the lengths, which A over B is equal to A plus B over A, which equals B, which approximates to 1.618. We will see why in a sec. The golden ratio can also be depicted through the golden rectangle, constructed out of a rectangle and a square that form a larger rectangle, in which the smaller rectangle is similar to the larger one because the ratio of the longer to the shorter side in both are equal. This ratio must be the golden ratio. Are Fibonacci and golden ratio related? Ratio consecutive terms in the Fibonacci sequence approaches the golden ratio B. Listed is the ratio of consecutive terms early on in the sequence. As we go down, the ratio gets closer to the golden ratio, and the value should converge to the golden ratio as n approaches infinity. As the Fibonacci sequence yields a Fibonacci spiral, the golden spiral is a self-similar spiral with a growth factor of E, the golden ratio. That is, a golden spiral gets wider by a factor of E for every quarter turn it makes. The Fibonacci spiral is an approximation of the golden spiral, since the ratio of consecutive terms in the Fibonacci sequence approaches the golden ratio. However, in contrast to the golden spiral, the Fibonacci spiral is not exactly self-similar, since its growth factor is still not constant. Here's an animation of the golden spiral, in which the spiral preserves its proportion as it is zoomed. Here is some history of the golden ratio. The Greeks understood that the divine proportion provides the most aesthetically pleasing composition. Constructed buildings that followed form of the golden ratio. Leonardo da Vinci illustrated the book De Divina Proportionate, translated to the divine proportion, which was written by Luca Pacioli. Many also think the proportions used in Mona Lisa follow the golden ratio. The Greek letter phi was adopted as the symbol of the golden ratio by American mathematician Mark Barr in the 20th century to commemorate the Greek sculptor Phidias. The Fibonacci sequence also appears in other plants. Arrangements involving consecutive Fibonacci numbers appear in a wide variety of biological settings. Three examples are presented here. In yellow chamomile, there are 21 clockwise curves. Showing blue, and going back to the Fibonacci sequence. In flowers, the Fibonacci numbers can be seen in the number of petals. For example, most daisies have 34, 55, or 89 petals. Most common flowers have 3, 5, 8, or 13 petals, all of which are Fibonacci numbers. Now, the Fibonacci sequence appears in other plants. Arrangements involving consecutive Fibonacci numbers appear in a wide variety of biological settings. Three examples are presented here. In yellow chamomile, there are 21 clockwise curves, shown in blue, and 13 counterclockwise curves, shown in a lighter hue. In pine cones, there are 13 clockwise curves and 8 counterclockwise curves. These are all Fibonacci numbers. The sequences are also seen in cauliflowers, where their tops look like a Fibonacci spiral. You can see the golden ratio in the human body. And golden spiral, which resembles the Fibonacci spiral, is evident ubiquitously, from natural phenomena to various plants to animals such as seashells and even to galaxies. Golden ratio is seen in the human body, for instance. The loop in some fingerprints follows the spiral pattern. Also, lengths of sections of fingers on the ratio of Fibonacci numbers. As well, you can observe how the look of ears resembles the Fibonacci spiral. Apart from nature, the golden ratio is used contemporarily in logos in modern design, such as Twitter's logo, which is formatted using the idea of the golden rectangle. In National Geographic's logo, figures of books are portrayed as a rectangle in the proportion of the golden ratio. Chevron, Pepsi, and other logos also follow the golden ratio. The golden rectangle is applied in layout photos, in which photos are arranged in the format of the golden rectangle, which was introduced with the golden ratio. As quoted online, while there will never be a one-size-fits-all approach for designing, there is a concrete mathematical approach that can help us get one step closer to creating amazing design experiences every time. The golden ratio. Now that we have related the golden ratio to the outside world, we'll derive the value of it. The golden number is a solution to this quadratic function because we can observe that the ratio b equaling a over b, which is also equal to a plus b over a, which substituting b over a as 1 over phi, we get this is equal to 1 plus 1 over phi. Now, when you multiply phi on these two sides, you will obtain the quadratic. Solving, we reach that phi is equal to 1 plus root 5 over 2. Because phi should be positive. Inverse of the golden ratio is negative 1 plus root 5 over 2, which is also phi minus 1. You can see this holds by taking this equation and subtracting 1 on both sides. The golden number is, in a sense, the most natural real number, since it can be written as this is a standard abbreviation for the continued fraction expansion of this expression. And the above follows directly from the equation we got for phi, which we can see holds up here because substituting this part for phi, because you notice that this part is equal to the whole part, gets this. It has to be phi since the expression is positive. Although the sequence is generated recursively, the Fibonacci numbers actually have a closed form expression, so they can be found from calculating the difference of powers of the roots of the quadratic we've seen. So here, B is the golden ratio, and C is the other root of the quadratic, 1 minus root 5 over 2. We will describe how to prove the expression. Although the formula seems complicated when given no context, once you understand the ingenious approach in finding this form, it'll come easier. First, we have conjecture that Fn is equal to A times b to the power of n plus b times c to the power of n, where b equals 1 plus root 5 over 2 and c equals 1 minus root 5 over 2. The definition of first terms of Fibonacci numbers, we can plug in our guess about the closed form expression for f0 and f1. Solving a system of linear equations gives a equals 1 over root 5 and b equals negative 1 over root 5. Now, assuming that fn minus 1 and fn minus 2 satisfy the closed form expression, we will show that fn also satisfies it. This is true because when we write Fn with the recurrence rule, and then we substitute the closed form expressions into this equation, we will eventually get this, which is closed form. Because v to the power of n minus 1 plus v to the power of n minus 2 plus v to the power of n. And similarly for c, which follows from the fact that b and c are roots of x squared equals x plus 1. So basically, these equations, such as is the quadratic equation, multiplied both sides by the root to the power of n minus 2. And similarly for c. Let's see interesting identities of the Fibonacci numbers. The sum of the first n Fibonacci numbers is equal to the n plus second Fibonacci number minus 1. This is easy to show by observing that when you list out the Fibonacci values from f1 to fn as the difference of its two successive numbers, summing up both sides gives the identity. Since the intermediate terms on the right-hand side are cancelled out. Two other identities are the sum of the first n Fibonacci numbers with odd index is the 2nth Fibonacci number, and the sum of the first n Fibonacci numbers with even index is the 2n plus first Fibonacci number minus 1. I'll give some time for you to try to prove them by yourself as an exercise. And for hint, prove them, implement a similar technique to what we tried together in the first example. So we use methods that resemble first example to the proofs we just went over. Okay, now as a few minutes have passed, probably some of you got some idea on how to solve them. If you didn't or haven't finished, you may think about them after the workshop or search up proofs on the web. An identity that has a beautiful visual proof is that the sum of the squares of the first Fibonacci numbers up to Fn is a product of the nth and n plus first Fibonacci numbers. So this we take a side length of the Fibonacci rectangle, say Fn. Let's choose in this case 21. And Fn plus 1 as the next side length. In this case, 21 plus 13, which is 34. Multiplying those terms up builds the area of the rectangle. Another way to find the area is to add up the areas of the squares constituting the rectangle. And this would be the sum of the squares from f1 to fn. The Fibonacci numbers can be applied to other mathematical structures, such as Pascal's triangle. You may have learned about Pascal's triangle, perhaps from previous math workshop. Basically, there are ones at the outer parts of the triangle, and the numbers inside are gotten by adding up the two numbers surrounding to the above. For instance, 2 is from 1 1 here. Just like the Fibonacci sequence, Pascal's triangle can go on indefinitely. The Fibonacci numbers are the sums of shallow diagonals in Pascal's triangle. If you take a look at the picture, shallow diagonals have common slope that is less than that of these diagonals, in which the first two diagonals or shallow diagonals have one term, the next two have two terms, and the following have three terms, and so on. Sums from each of the shallow diagonals are progressing following the order of the Fibonacci sequence. I'm not going to go over proof in this workshop, but you could look at it and kind of get some sense why it works, and also learn it after if you would like. A problem that can be solved with Fibonacci's recursion is enumeration compositions, which is counting the ways to divide a number into ordered groups of ones and twos. We can map this out with a number of ways for a person to climb the staircase with n steps, taking either one or two steps each time. It turns out that there are f5 plus 1 or f. It turns out there are fn plus 1 ways of writing the given number n as an ordered sum of ones and twos. For example, there are f5 plus 1 equals f6 or 8 ways when you climb the staircase of 5 steps, taking one or two steps at a time. Here lists out the enumeration in this form for the fives. And you can see that this holds for any number of steps. For one step, you'll have that there's one way to climb the staircase. F2. And for two steps, there are two ways. Either go one step at a time or go two steps directly. And that is equal to F3. For more steps, we can perform casework based on whether the person starts by taking one step or two steps. So in this case, let's n where n is more than 2. So the number of ways to reach the top starting from one step is the number of ways to climb n minus 1 steps. The number of ways to reach the top starting from 2 steps is Sn minus 2. Summing them up, assuming that the Fibonacci relation holds for n minus 1 and n minus 2 steps, results in Fn plus 1 ways to climb n steps. You can see that the sequence of S terms is simply a shift one from the Fibonacci sequence. There is a generalization to the Fibonacci sequence, which produces negative Fibonacci numbers. The Fibonacci search technique is a method in computer science of searching a sorted array using the divide and conquer algorithm. Instead of dividing into two equal-sized parts in binary search, the sorted array is divided into two parts of sizes based on consecutive Fibonacci numbers. So this is a practical application wielding the Fibonacci numbers. So here's a demonstration from an ordered set array of numbers. The goal is to find I such that the value at index I is X. So we start with the smallest Fibonacci number. Is no smaller than the array size. In this case, if the array size is 11, we'll go with 13. Then we'll set the index to F minus 2, which we will then use this number and check X on the array of one of the indexes F minus 2. And then if X is equal to that, we return the index and we're done. However, if X is smaller, we'll go to Fibonacci numbers down from that, and we don't check this script. Whereas if X is larger, you don't have to check the first part, you will cut it to this part to check. Then we repeat the process. And compared with binary search, Fibonacci search leads to about 4% more comparisons on average. But has the advantage that only addition and subtraction are needed to calculate the indices instead of bit shift or division binary search. A generalization to the sequence is when the Fibonacci sequence can also be extended to negative indices using the rearranged relation in which a term is equal to the difference of its two successive terms. So the bidirectional sequence is given here, which extends in both directions onward. It can be observed that F negative n is equal to -1 to the power of n plus 1 times fn. See how it works ourselves for a while. Here's another sequence that follows the same rule as the Fibonacci sequence. Lucas numbers start with integers L0 equals 1 and L0 equals 2 and L1 equals 1 and follow the same recursion Ln equals L minus 1 plus Ln minus 2. In taking these terms of the Lucas sequence, we can also construct a continuous golden rectangle. And since it involves the same recurrence relation, the ratio of consecutive terms in the sequence would converge to the golden ratio. Hence, the Lucas spiral, the Fibonacci spiral, and the golden spiral look similar. Here are other generalizations. So they are similar to the Fibonacci sequence in that they are recursive, but they follow slightly different rules. The L numbers follow Pn equals 2, Pn minus 1 plus Pn minus 2. So the coefficient of Pn minus 1 is 2 instead of 1. The Fibonacci polynomials is an extension of the Fibonacci sequence with polynomials, which is f and of x equals x times fn minus 1 of x plus fn minus 2 of x. Shadow numbers and pair numbers follow p of n equals p of n minus 2 plus p of n minus 1. And similar to the Fibonacci and Lucas numbers, the pattern numbers can be shown geometrically with equilateral triangles. There's also n-step Fibonacci numbers. It basically follows the Fibonacci terms, except you add different number of terms right before it. So Fibonacci numbers, they have it's two-step, but it could also be next numbers, sum of 3 previous numbers, which are Fibonacci numbers, or 4 previous numbers, kept Fibonacci numbers, and so on, 5, 6, going on. That concludes our presentation. Anyone have questions? Okay, about fingerprint. Yeah, that actually I don't really know much about, but I guess just it said that the fingerprint is similar to the loop. Okay, Charles, do you have any questions? the chat. Okay. Um, is this going to be a pre-calc? Well, I'm actually not sure. Usually though, I think part of my math workshops such as Pascal's and Fibonacci numbers do not like that's common in general math curriculum, but sometimes in middle or high school they throw some interesting stuff in, such as Fibonacci numbers. You don't have to worry about that for school. Okay, I guess that that's it. Thank you for attending this workshop to support Doggy STEM. I hope that you found this workshop insightful, have dug deeper into the Fibonacci sequence. Be sure to check out other fun math workshops. There is one coming up featuring Graceland on cryptography, and it's a cool application of math. And you're welcome, everyone. So if there's no more questions, that's it. I'll let you guys go early. Have a good night.